So this lecture, and I'll spend some time on this slide here, it is about pH. And I spent a lot of time trying to figure out what is the connection between all this stuff anyways. And we've been talking about making things like IV products, ophthalmic solutions, where you're going to have your drug in solution, and you're going to apply that solution to the eye or into the blood directly on these biologic solutions, and that's why we've been talking about isotonicity. But it makes sense too that a lot of your drugs that you're going to dissolve and disperse in your liquid are either weak acids or weak bases, and when you put them in water, they will change the pH. And you don't want the pH so much to be too acidic or too basic where it's going to cause irritation, so you've got to be concerned about the pH there. But there's also something also more important that I'm not sure that people appreciate, that I put all these pictures on here to kind of get at, is the whole point of ionization. So to realize for a drug to be absorbed across a biologic membrane, so for it to go from the inside of the stomach to be absorbed through the epithelial layers and through the stomach and into the blood, it has to pass through the cells. And if it is charged, if it has separated and it is ionic, okay, then it's not going to be absorbed very well. It's essentially the non-ionic or the non-ionized form of a drug that actually can be absorbed and utilized. So would you agree, depending what will determine whether or not something in solution is ionized or not, a large part of it is the pH, okay? And relating the pH to the pKa, those are the take-home things that we're going to have to be able to know, is calculating pH, pOH, and understanding the relation then of the pH to the pKa is very important. So let's just talk about that. And I'll use this, I'll start off, well, let me just start off with this one. I really love that picture here. It helped me a whole lot. Because let me ask you, what's the difference between a weak acid and a weak base? I'm sorry, that's stupid. Weak acid and a strong acid. A strong acid is something when you put it in solution, it completely dissociates. You take from the acid molecule and all you get is all ionized. There's nothing left, no parent molecule left. Weak acids don't always completely ionize. And so some acids, though, are a little bit stronger at ionizing and coming apart. Other ones are not. So the point here is it's this cutoff line right here about the pH versus the pKa. And we'll define pKa as the dissociation constant for acids here in a little bit. But when the pH equals the pKa, then there's no net movement between unionized and ionized. It's all in equilibrium. Therefore, when pHs are lower than the pKa for acids, therefore very low, then they tend to be unionized. Okay? So unionized can be absorbed. But when you raise the pH from this acidic level up through to a higher pH value, once it passes its pKa, then it will start to ionize and you'll have less and less of it be absorbed. Okay? So pH less than the pKa for acids is non-ionized and absorbable. When the pH is above its pKa, then it becomes ionized and you'll have less absorption. Unfortunately, it's the exact opposite for bases. So at low pHs, an acidic pH and a low pH for a base, it's going to be ionized in the beginning. It's not going to be really non-ionized until you exceed its pKa and become at a higher pH, and then it becomes unionized. So that's why you can see the line for the base is opposite of the line for the acid. Okay, and again, I still kind of emphasize the relation between the pH and the pKa is so that you can understand how much of it is absorbed. And so there's kind of this example here of, I think I used this was kind of an aspirin example of a weak acid. If you look on the right-hand side in the stomach where you have a relatively low pH, okay, essentially then the acid, the other acid that's there is going to keep the aspirin from ionizing, keeping the hydrogen molecules from coming off the aspirin, so it'll stay non-ionized, okay? Because all that acid, it keeps it, it's a low pH, it's lower than the pKa, so it doesn't ionize, it stays non-ionized, and it can be absorbed. But look what happens, and so you can see here, and very little of it is ionized in this low pH. But when it crosses over, therefore, and becomes absorbed into the blood has a much higher pH, a pH closer to 7. Well, that pH is now above the pKa for that drug, and it starts, there's not as many hydrogen molecules, so it starts releasing its hydrogen, it starts to become ionized, and you can see that it goes from less than 1% all the way up to 9%. So the whole take-home message here is, and it's important in a minute here to understand, pKa as it relates to how much of a drug will become ionized versus unionized. And the reason we're talking about this again is that it's important. The only reason I showed you this kind of example here is it goes to show whether it's an acid drug or a base drug, where it gets absorbed. When you swallow a pill, does it get absorbed in the stomach? Does it get absorbed in the intestine? How much of it gets absorbed? It differs by drug, right? And a big thing that we're trying to talk about is the pH. Would you agree the stomach pH is definitely lower than the intestine pH, which is definitely higher. Therefore, some drugs are absorbed a little bit more in the stomach. Some aren't absorbed in the stomach, but get absorbed really well in the intestine. And part of that difference is the change in the pH as you go through the digestive tract. And that's kind of the rationale why some of this is kind of important. All right. Now, I'm not a chemistry teacher, and I'm not here to teach you all your acid and base. You hopefully have learned a lot of that already. This is hopefully a review, and hopefully get you the mathematical skills you need to do well on the questions that you'll see on the test. So, some fundamental background. Let's just make sure you understand what pH and pOH is and how you could actually calculate that. All right. So, this is hopefully a review. It says, a pharmacist dissolves 150 milligrams of sodium hydroxide with a molecular weight of 40 in enough water to make a total of 500 milliliters. What would you expect the pH to be, high or low? And to answer that question, you actually got to know what the pH is. So we're going to have to calculate the pH and then decide, is it high or low? And what's the cutoff? What do we say a neutral pH is? Just making sure it's a low review. 7. So less than 7 or values smaller than 7 is more acidic, and as you get greater than 7, you'd be considered more basic. So with that, how do we calculate the pH? All right. Well, first you got to kind of understand what kind of drug is sodium hydroxide. The formula NaOH, all right, it's actually a very strong base, meaning that when you put it in water, the sodium completely, every molecule, every parent molecule dissociation produces one sodium ion and one hydroxyl ion, okay? So that's what you're forming, all right? So what is, okay, so those are our concentrations. We have a certain amount of this, and that will then produce two things from the parent molecule. All right. Well, what is pH and pOH? Hopefully, I remember this, the little p. What does the little p stand for? The negative log of some concentration. And for pH and pOH, the trick is to remember the concentration has to be in what units? Molar. It has to be moles per liter. So you're going to take the negative log of the molar concentration. And if it's of the hydrogen ion, it's pH. If it's of the hydroxyl ion, it's pOH. All right. Just remember, get the concentration of either one of those, H or OH, into moles per liter. Then take the negative log of that. That's how you make a pH or a pOH. Okay? And then the last relationship to remember of pH and pOH is this. pH plus pOH is equal to what? 14. Okay? So the two added together equal 14, which means you can solve for either one of those, since we oftentimes want to measure pH. Obviously, then we can say pH is equal to 14 minus pOH. So that's where that comes from. Okay? So you know how to answer this question now? Well, we know how much sodium hydroxide. Does sodium hydroxide produce hydrogen or hydroxide? Hydroxide. So let's calculate the molar concentration of hydroxide that's produced, and then we can calculate our pOH, and from the pOH we can solve for pH. Do we have a plan there? So it's not very difficult. Let's just set up what we have. We started with 150 milligrams of sodium hydroxide, right? That's the weight of the sodium hydroxide. And it was placed in what volume? Come on. 500 milliliters. All right, so I want to make sure you can see where all of that stuff comes from. We start with 500 milligrams sodium hydroxide over 500 milliliters of solution. All we need to do is change our units, because what units do we need to be in? We need to be in molar concentration, right, which is in moles per liter. So you can change any of those units you want, but I started with the weight. So the first thing I did was convert from milligrams of sodium hydroxide to grams by multiplying by 1 gram over 1,000 milligrams. So as everyone see, first thing I did was convert milligrams of sodium hydroxide to grams of sodium hydroxide. Then I multiply and convert from the weight of the sodium hydroxide to the number of moles. And you all know this, right? How do you convert from grams to moles? Molecular weight. It's the molecular weight in grams is equal to 1 mole. Therefore, I multiply by 1 mole over 40 grams. Since that's the molecular weight, my grams cancel. I'm now in moles of sodium hydroxide. Everyone okay so far? Then to convert to hydroxide, the only trick is you've got to look at this formula up here. If I have one of these, how many of these do I get? 1 to 1, right? I get 1 hydroxide for every 1 sodium hydroxide. So I can multiply by the fact that there's 1 mole of OH for every 1 mole of sodium hydroxide. That way sodium hydroxide cancels, and I'm actually in the number of molecules of hydroxide. All right? And in the units of moles. So far so good? But it's not, but I'm what? I'm in moles per 500 milliliters. So don't forget, we got to fix our volume. So that's why my last step was to multiply by 1,000 milliliters per liter so that I can cancel my milliliters, and my only remaining units are going to be the moles of hydroxide and liters in the denominator. So if you do that math all the way across, and you get 0.0075 moles per liter. All right? Well, that's easy breezy now. pOH is equal to the negative log of the hydroxide concentration. Let's take, and if you haven't done it, take your calculator. And this is where I'm saying about practicing your calculations, using your calculator. In this chapter, you have to use, this section, you got to use your log key. You're going to have to use a couple of different things here that you may not normally do. So make sure you're okay with, take the negative log of 0.0075 and see if you get 2.12. All right? That's what you should get. And while we're doing that real quick, here's an important number. While you got your calculators out, this is something you just got to help you understand. What is the log base 10? And again, we're always, for this, all of the things we're doing, it's in base 10, not natural log base 10 of 1. What is the log of 1? 0. Therefore, now do this, what is the log of a number less than 1? Do 1/2. What is the log of 0.5? I don't care what the number is, since 1 is 0, anything less than 1 is going to be a negative value. So you get negative results when you take the log of something that's less than 1. When you take the log of something greater than 1, you get a positive value. You'll see why that plays a role here when we do our molar ratios here in a little bit. But I just thought I'd point that out since you're playing with your calculator there. You can practice that a little bit. All right? So let's just finish it. So our pOH is 2.12. Is that our answer? No, we want pH, right? So let's finish it up by saying pH is equal to 14 minus pOH. So we would do 14 minus 2.12. Result would be 11.88. Is that a acidic value or a basic value or a neutral value? That's basic, right? Anything greater than 7, certainly that much greater than 7, I would consider that a basic pH. Okay? Let's move on. As it gets more difficult, let's talk about the dissociation of weak acids. We're leading up to the Henderson-Hasselbalch formula, and you have to know that one. It should not be the first time I've said that. So to understand that formula, let's start with weak acids. And in this case, we're going to say this is the weak acid. So HA is the normal way that they abbreviate an acid. Okay, it's basically the proton donor. So the acid is HA. It will dissociate and produce a hydrogen ion, and oftentimes you'll see this referred to as a conjugate base. I hate that term. You'll notice in my lecture going forward in my slides here, I call it the salt. I like to call it the salt versus the conjugate base. So it produces a hydrogen ion and a salt. We started with an acid, and what do we produce to the right-hand side? A hydrogen ion and a salt, okay? So again, in your own mind, if you learn this already and like the word conjugate base, go for it, but I kind of prefer to teach it this way, all right? Well, what is a Ka? Ka just stands for the dissociation constant, and it really is a measure of, okay, if you've got equilibrium, would you agree this arrows are going both directions? That means there's some degree of going to the left of the thing and some degree going back to the right. It goes back and forth, so it's an equilibrium. How far to the production of the products does it go relative to the number of parent molecules we start with? How much dissociates? That's kind of what the Ka does. It measures then the concentrations of the products, whether it's the hydrogen or the salt, divided by the concentration of the acid to begin with. So just looking at this molar ratio, and this is, once you understand this in a little bit with the Henderson-Hasselbalch, going to make things easier. The larger the Ka, the what? What does a larger Ka mean? Let's compare it to 1. Let's just say if the Ka was 1, that is, if you had exactly the same concentrations on top as you have parent molecules, so the concentrations were the same, then that ratio would be 1. If it's greater than 1, then you're producing more products, it's shifting more to the right. If the value is less than 1, then you still have more parent molecules than you have the production of the products, all right? So it's just something to kind of keep in mind. All right, no one like that. All right, pKa. Ka, when you do this with actual values, the Ka value is a really small number, something times 10 to the negative something. Those are difficult and easy to mess up. So instead of just using the Ka as the actual value, let's do a pKa. What does a little p mean? Negative log of. So that's why we normally take the Ka and do the negative log of it to express it in a more normal number, okay? So that's what a pKa is. All right, so, is that not working again? Thingy. All right, so what's important? Let's get to the Henderson-Hasselbalch. This is the formula on the bottom that you will be using in a majority of your formulas here in this thing. So make sure you understand it and can use it. So it basically says that the pH, you can measure the pH of any solution by knowing the pKa of the acid and adding to it the log base 10 of the concentrations of the salt, which we said was the A minus, divided by the concentration of the acid, which was the HA. So it's salt over acid. Put a star by that. You got to remember that because it's different for bases. Make sure you understand this. This base is different, but the big difference with the base is it inverts that proportion. So for acids, it's salt over acid for the concentration. And since it's in brackets, remember we're always going to want to use molar concentration. So it's the molar concentration of the salt divided by the molar concentration of the acid. Okay? And that is everyone's favorite Henderson-Hasselbalch formula. Okay? So, oh, I can't use it. Let's move on to bases, and I'll try to go through this quick here just to kind of get to the same point. Bases are very similar. You start with a base that has a hydroxyl on it. You put it into water, and it dissociates, essentially freeing up a salt. In this case, the B plus is the salt. The hydroxide is the thing that's freed up, and the base, the BOH, stands for the base. So in this formula, to get down to the Henderson-Hasselbalch, the concentration of that's your initial base, the BOH, is the base concentration. And the B plus is considered the salt now because it's the part that's released and freed up to the hydroxide ion. All right? Now, you don't measure a Ka for bases, you measure a Kb. It's the same thing, but it's a Kb, and you take the salt concentration times the hydroxide over the concentration of the parent base, so that's set up the same. You still refer to it as a pKb, and let's just get down to make sure you understand. This is the important formula that's analogous to, but not exactly the same as the Henderson-Hasselbalch for the acids. So, in this case, and the derivation is shown, I don't want to go through all that, pH is equal to, for a base, 14 minus the pKb. So if you have the Kb, you're going to be 14 minus the pKb, plus the log of, now this is where it's changed. Did you pay attention? It's the concentration of the base over the concentration of the salt. So the salt has flipped, all right? Still molar concentrations, and there you have it, okay? So those two formulas, the Henderson-Hasselbalch certainly for the acids, and the Henderson-Hasselbalch for the base, are they similar? Yes. Are they exactly the same? No. Do you need to be able to make sure that you're aware of and use the right formula and set it up the right way? Absolutely. So those are the real tricks to the equations that we're going to use here in a minute. Okay? So let's go back to the acid and use the Henderson-Hasselbalch and really think about this molar ratio. It really is actually kind of helpful once you understand it. Okay? So this question says, what is the molar ratio of sodium acetate to acetic acid? And whenever you read these questions, I like to immediately identify what's what. Okay? So in this question, the acetic acid is the acid, and sodium acetate is the salt. What's a good trick to kind of realizing which one is the acid? The one that has what in the name? Acid. That's helpful. And the one that the salt that has sodium in the name, that's also kind of helpful to kind of get that as well. So I'm just trying to say, figure out, even before you worry about any of the numbers, in this combinations of things, which one is going to be my hydrogen ion donor, which one's going to be my hydrogen ion acceptor. In this case, acetic acid is the acid, and sodium acetate is the salt. So it's what is the molar ratio of those two things that would be required to prepare a buffer solution with a pH of 4.5. Okay, well, that's what we want. We want the pH to be 4.5, and the two ingredients we have are sodium acetate and acetic acid. By the way, the pKa of the acid is 4.05. Which one did we say the acid was? Acetic acid. So acetic acid's pKa is 4.05. So do you have any formula that relates pH to pKa to relative concentrations of acids and salts? That's the Henderson-Hasselbalch, right? That's what we're practicing using. So let's set it up. In fact, there it is again. And we have almost all of the variables that we need to plug into that. So using that formula, let's see, what is the pH we want to make? We want our buffer solution to have a pH of 4.5. So that's why we set that there. What is the pKa? We were given the pKa of the acetic acid to be 4.05. So those come directly from the question. And what we don't know and what we're solving for is the ratio, the molar ratio of the salt to the acid. So if we put 4.5 equals 4.05 plus log base 10 of salt over acid, then all you have to do is subtract 4.05 from both sides. So do you see that you get 0.45 on the left equal to log base 10 of the concentration of the salt over the acid? Is that easy? I hope. Now here's a little bit of a math skill that some of you may still struggle with a little bit. What is the opposite function of a log, base 10? How do you cancel a log base 10? Right? We got to get rid of that function. To solve for the salt over the acid, we have to cancel it. Does anyone know? Do you remember how to cancel a log base 10? The inverse function on your calculator is 10 to the x, right? So now all we need to do to cancel the log, on both sides, let's do 10 to the x. So on the left side, it would be 10 to the 0.45 equal to 10 to the log base 10 of the salt to the acid, right? So we can actually, in your calculator, solve for 10 to the 0.45. That's a number. It turns out to be 2.82 once you put it in your calculator. That would be equal to, then, remember, the 10 to the x and the log cancel, and that would just leave you the salt over the acid as a concentration, right? And that's our answer to this question. So the molar ratio of salt over acid is 2.82, right? Questions on that? Why would we ever do that? Well, why is in the next slide. So let's continue on. That was half the question. But we now know that the molar ratio is 2.82. We know the salt to the acid in this buffer solution has a molar ratio of 2.82. Knowing that, and knowing that we're going to want to make a buffer solution with a total, so circle the word total there, it's kind of important, a total concentration of 0.02 molar. How many grams of the sodium acetate and how many grams of the acetic acid would you need to prepare a liter? Right? That's why we needed to know that. You're going to see that here in a second, okay? Because I know what the total is. Let me just make sure. Total of what? What are the only two things in this solution? Sodium acetate and acetic acid. Those two things added together, the total concentration of everything is 0.02 moles per liter. What I want to know is how much of that is going to be the acetic acid and how much is going to be the sodium acetate. So how can I relate those two together? And this is kind of a tricky question, I think. It starts with the molar ratio. The thing that I have that kind of relates the amount of salt to the amount of acid that I need in this solution is that molar ratio. And we said that the salt over the acid was equal to 2.82. All right? So bear with me. Think of this as two variables. We have the salt, which I would say is like y, and let's say that the acid is, well, I didn't change my color, man. X. Oh, it's not working. Okay, so anyway, so we have salt over acid is equal to 2.82. What we need is to solve for one of those or the other. We can't have two variables kind of in the same place. So let's just solve for the salt. If I solve for just the salt, couldn't I say that salt is equal to 2.82 times the acid concentration? You see where I just canceled this out? I basically just moved this over here, and that's how I get this over this. Basically, this is like saying y is equal to 2.82x, okay? I'm just trying to show that I know I have acid in the word salt, but you can treat those like unknown amounts. You can treat those like variables. So essentially, we've re-expressed y over x equals 2.82 as y equal 2.82 times x. And basically what we have is the salt is equal to 2.82 times the acid. Are you okay with that? Because if you don't get that, then everything else is lost. It gets real easy once you understand that. Since we had acid, or salt over acid equals to 2.82, you can say salt is equal to 2.82 times the concentration of acid. Why is that important? Because let's go back here. Remember I said total was important? Basically, the total buffer concentration are the two things added together. So we know that the acid concentration plus the salt concentration is what equals the 0.02. Once again, I don't want two variables, so let's substitute all of this over here for the salt, okay? So if you do that, then that would be acid plus 2.82 acid equals the 0.02, okay? We just substituted the value for the acid, with the salt, with its expression as an acid, which was 2.82 times its concentration. So now this becomes something like x plus 2.82x. So what do you get when you have x plus 2x? What does that equal? 3x, right? So it's the same thing here. Acid plus 2.82 acid is how many acids? 3.82 acids. We just added it together, right? So now I've got 3.82 acid equals 0.02. If I divide each side by 3.82, then I can tell you the acid concentration is equal to 0.00524 molar, okay? Kind of algebraically, would you agree? Just think of it, though, if you can kind of set it up. I don't want to get rid of my scribbles. I don't think I make anything better. All right, so is everyone okay up to here? All right. So we now know the acid concentration. That's the hard work, because now to go back to the salt concentration, it's easy. We said that the acid plus the salt equals 0.02 molar. I now just found out that the acid is 0.00524, so all I got to do is take this amount that I just saw for acid, put it up here in the formula, and then I just say 0.00524 molar plus salt equals 0.02. Just subtract that, and you see that the salt is equal to 0.01476. That's the easy part. Would you agree? Solving for the original acid concentration took a little bit of work. Once you know the acid, then since the acid plus the salt is equal to the total, you can just subtract it to find the other. And frankly, we're almost done. We now know that what I need to make this is I need to have the salt, which is the sodium acetate, at that concentration, and I need to have the acetic acid at the 0.00524. But the question wants what? How many grams? Okay, so in the end, my last step is to simply take my concentration. For example, I started with the acetic acid, and you just told me that the acetic acid needed to be 0.00524 molar, which is 0.00524 moles per liter. And if I want to know the grams per liter, all I need to do is convert moles to grams. And how do you convert moles to grams? By multiplying by the formula weight. So remember, we were told for the acetic acid, its molecular weight was 60, right? So if I put the 60 in here and take its moles times 60, moles cancel, and I get grams per liter. So if I do 60 times that little bitty number, I get 0.314, what are the units? Grams per liter. And everything was in per liter, so I didn't have to mess with the volume. Same thing with acetic acid. Remember, there was the salt concentration, so I put it down here. Remember, here's the molecular weight for that, so that's where that comes from over here. Multiply it by the molecular weight, and you've converted your moles to grams. And that's your answer. Those are the two concentrations of your two things, the acetic acid and the sodium acetate, where if you have that many grams per liter and you mix them together, you would have a total concentration of 0.02 molar, and essentially you would have a pH equal to what we decided, which was the 4.5 in the previous question. Kind of cool to try it together. All right. So that was kind of an important one. So these two questions go together. And again, ignore my scribble. The idea of being able to use the molar ratio to basically then determine the components of a buffer solution, to determine how much of the acid part of it versus how much of the salt part. The Henderson-Hasselbalch, being able to do that to determine how many of the relative amounts of the two parts to your buffer solution is kind of an important question. All right? Now, where we're going here is once you have that, so you've got your buffer solution, whether it's acid or base, you've got a certain amount of acid or a certain amount of base and a certain amount of salt. Okay, so one or the other and then the salt. What happens? Why do we have buffer solutions? Why? To help maintain something at a pH, but also to help minimize changes in pH. Because when you add acids or add bases, you want your buffer solutions to basically gobble that up and to avoid making large changes in pH. So what happens when you take a buffer solution, and in this case, add this strong base? So let's start with an acid-based system where we've got an weak acid and a salt. Okay? We've got our Henderson-Hasselbalch here, so I can relate the pH to the pKa to my two concentrations, but now I dump in some of my strong base. What will the base do? The base will react with what? The salt or the acid? The acid. Okay, when I say react to it, the acid acid will neutralize the base, okay, and form what? What happens when an acid reacts with a base? It then forms the salt. All right, so what we're trying to say, this is important. When you add if you're going to start with an acid situation, then when you add a base, then what we're going to do is calculate the new or revised concentrations. So when you add a base to this solution, the base is going to use up the acid. So what happens to the original acid concentration? It goes down by the same molar concentration as the amount of base that you added. So the concentration of the acid is reduced by the molar concentration of the base. But remember, the original salt is going to be increased because that's what you do when you react the base with the acid is you form the salt. Therefore, your salt concentration is going to be increased by the molar concentration of the base that you added. Okay? So essentially, when you have these types of questions, first calculate your revised concentrations and then use the Henderson-Hasselbalch the same way it always is. It doesn't change the Henderson-Hasselbalch. Adding a strong acid or a strong base to a buffer solution, first, just figure out how that changes the concentrations, and then use the same old Henderson-Hasselbalch to calculate what the change in pH was. Okay? So that is what happens when you add an acid or a base to an acid. So let's kind of do this. The question, it says, what is the change in pH on adding 0.02 moles of sodium hydroxide to a liter of the buffer solution containing sodium acetate, 0.5 molar, and 0.5 molar acetic acid? So again, which is our salt? This is going to be our salt. Here's our acid. What are the relative concentrations? We have a starting concentration of the two are the same, But what we're adding is this concentration of a strong base. All right? So how would you approach this? Did you guys do it? First of all, the question asks for the change in what? pH. To know what the change in the pH is, wouldn't you need to know what the pH is to begin with? Could we calculate what the pH is even before we add the base? Yes, that's what you need to do. What formula would you use to measure or determine the pH of a system? The Henderson-Hasselbalch. All right, so let's make sure we use the right formula and use the formula for an acid, since our buffer solution before we add any base has acetic acid and sodium acetate, so it has an acid and a salt. So the pH is equal to the pKa plus the log of the molar concentration of the what? Salt over the acid. So let's put in what we know. Do we know the pKa for acetic acid? There it is. All right. Do we know what the concentration of the salt is? That's this one right here. There's the concentration of the salt, and here's the concentration of my acid. All right. So all I have to do is put all of those numbers into this formula, and this is where the math skills and using your calculator is important. Does that make sense? So again, I doubt you'll have to have the formula memorized, or you can write it down on your little note card. It isn't about memorizing the formula. It's about correctly performing the math and substituting the values in the right spot. So does anyone have any questions about where the numbers came from for that formula? Then you should just be able to solve for it. So you get 4.76 plus. Well, this is what I was getting to before. What is 0.5 divided by 0.5? It's 1, right? What is the log of 1? 0. So in the end, we added 0 to the 4.76, and that's where we ended up with the 4.76 altogether. Oh, Larry. Any questions about that part? So what did we do? All we've done so far is to show you that the pH before we did anything to this solution, to this situation, was 4.76. Now we're going to add the base. And before we worry about the Henderson-Hasselbalch, we got to decide what does adding the base do to my concentration of the acid, and what does it do to the concentration of the salt. We said in this system that a base will do what to the acid concentration? Will reduce it. Remember, it will subtract that molar concentration because it will chew up or use up the acid. So let's take our original acid concentration, which we were given, right, at 0.5 molar, subtract the concentration of, and again, it needs to be in the same units. Be careful. If we're in molar, we have to subtract molar. And we were told 0.02 moles per liter. So what does that equal to? That's molar. It is the same thing, but just make sure 0.02 moles per liter is 0.02 molar, so we can subtract that. So 0.5 minus 0.02 equals the 0.48 molar. That is our new concentration of the acid. What is our new concentration of the salt? The salt isn't going to go down, the salt is going to go up, because that's what we're forming in this sort of reaction with the base with an acid. So again, we'll take our original 0.05 molar, add to it the amount of base, which was the 0.02 molar. Therefore, the salt concentration is higher, and it's now 0.052. So do you see where the new acid concentration came from and why it's lower? Do you see where the new salt concentration is and why it's higher? That's because the base reacted and chewed up the acid to form the salt. Now, let's just go back and use the same Henderson-Hasselbalch formula, but with our new situation, with our new concentrations. So again, we still have the pKa at 4.76. We're going to add to that the concentration, the molar concentration of the salt over the acid, but now the salt is 0.52 divided by 0.48. And without even doing the math, is 0.52 divided by 0.481? No. Is the numerator higher or lower than the denominator? Higher. So is the value going to be greater than 1? And we said the log of values greater than 1 are positive. Would you agree? When it ends up, and you'll see here in an example, when it's lower, that you end up getting a value that you subtract. But in the end, if you just do the math, Larry, just do that math, you can see you get 4.76 plus 0.03. And that's the value you get when 0.52 divided by 0.48, and take the log base 10. Then it's 0.03. You add those together. Your resulting pH after you've added the base is 4.79. That's still not the answer to this question. This question wanted the change, right? So the last thing to do is to take where you ended up at. So the change means where did you end up with minus where did you start from. That's the change. So 4.79 minus the 4.76 means we increased. You can see the value is positive. So the pH was raised. It's higher. It went up to by 0.03 pH units. Okay? You want to do it again? Oh yeah, I can see you want to do this again. Let's do it again, but now let's do it with the base. And I'll go a little bit faster with this because it's the same idea. There's our friendly wasp up there. Let's do it with the idea, though, that if you've got a base, and again, so in a situation of a buffer solution where you've got a base and a salt, there's always a salt with either an acid or a base. In this case, with the base solution, we've got a base with its salt. All right? What happens when you add a strong acid? It's the same idea. What does the acid react with? The base. So the base concentration is going to go down. When an acid reacts with the base, what do you end up forming? The salt. So the salt goes up. All right? So do you understand that the change in the base concentration goes down, the salt concentration goes up for the same reasons we talked about? I hope that's clear. The only other trick is to remember to use the right formula. Since we're talking about bases now, you got to use the different Henderson-Hasselbalch. So now pH for a base is equal to the 14 minus the pKa plus the concentration. Put a star by it. I know some of you are going to mess this up. When we're doing base concentrations, it's the what? It's the base over the salt, not the salt over the base like it is for the acid thing. Okay? So, but once you have that, use the right formula, it's just as easy to solve as the one we just did. So let's do it. It says, what is the change in pH when adding 0.01 mole of hydrochloric acid to a liter of buffer solution containing 0.05 molar ammonia and 0.05 ammonium chloride? All right, so which is the base and which is the salt? Again, the chloride here is the tip-off that that's going to be the salt. The ammonia here is going to be the base. All right? So now that we know that, how would we do this? Let's do it the same way. The only trick is that I gave you the KB instead of the what? PKB. So we got to have to also do that a little bit of math with that, but you guys can handle that. So remember, you start by determining what the pH is before you add the acid. So before you mess with the acid, let's just determine the pH of this solution using the Henderson-Hasselbalch formula. And that's 14 minus the PKB. So remember, we were given KB, so what is the PKB equal to? The negative log base 10 of the 1.8 times 10 to the negative fifth. All right, so that's where that came from. Is everyone okay with this value here is the KB that we're sticking into that negative log formula? Yes, question?
Just in the slide before, it said 14 minus pKa. Should that be pKa?
Yes, thank you. Yep, no, thank you. Typo. Thank you so much. In this formula, thank you. That's perfect. So is that everywhere clear? Going back to the earlier one that I said it or showed it to you, but the formula for a base should be 14 minus the pKb plus the log of the concentration of the base over the concentration of the salt. Thank you. You're absolutely right. So setting this up, though, so we did set this one up the right way. It is going to be minus the pKb, all right, plus the log of the concentration of the base over the salt. All right, so since, again, this is going to be equal to 1, that's where we get the 0 from. And again, if you take the negative log of 1.8 times 10 to the negative fifth, you get 4.74. So 14 minus that plus 0 gives you 9.26. So does everyone see, before we do anything, our pH of this solution, before we add any of the hydrochloric acid, is 9.26. Next step is to determine the revised concentrations. So remember, the concentration of the base is going to go down by the same molar concentration of the acid added. And since we added 0.01 molar or moles per liter, that's 0.1 molar. So our original 0.05 minus that gives you 0.04 molar for the base. Now for the salt, since it's going to increase, again, just remember the base is going down, but the salt is going to go up. So the salt is 0.05 initial plus the concentration of the acid we added, which is 0.01. So we now have a 0.06 molar concentration of the salt. Let's go back to that same formula now, and it's 14 minus, again, the KB isn't changing, so it's still minus the 4.74, but we still add to it the log of the base over the salt, which is now 0.04 divided by 0.06. Is that 1? Is 0.04 divided by 0.06 1? No. But now, is the numerator smaller than the denominator? So is your value going to be less than 1 when you do that division? So what would you predict the value to be? Negative. So that's why you'll notice when you do the math, it ends up being a negative value because your molar ratio is less than 1. So just helping you kind of see the trends when you do the math. All right? So by the time you do all of that, 14 minus 4.74 minus 0.18 from solving that log, you get 9.08. And remember, to calculate the change, which was this question, you take where you ended up at, which was the 9.08. You subtract from it where you started with here, so 9.08 minus 9.26 means we had a decrease in pH. The pH got lower by 0.18. All right? All right, so we've talked about using the Henderson-Hasselbalch to be able to determine the concentrations of buffer ingredients. We've now also been able to use the Henderson-Hasselbalch to predict what happens when you have a buffer solution that you add an acid or add a base to. So those are the two main things so far. And then lastly, and I think this is the last question, and it's the most important. I love this one. It ties it all together, and it brings together why we studied this pH at the same time we talked about isotonicity. Because our point to all of this is we're talking about making liquid medications from solids, and these liquids being applied to the eye or being used IV need to be sterile and isotonic and essentially buffered at a reasonable pH. We have to account for the pH, we have to account for the tonicity, and again, we have to sterilize those products, all right? So this question brings all that together. And it also brings up the fact that, in practice, I ain't making my own buffer. I got better things to do with that. I'm buying. So who's got the cheapest buffer out there? Sorensen's. I won't call it cheap, but it's very commonly used. There are commercially available buffer solutions. You don't have to start from scratch every time. So let's use that. So Sorensen's phosphate buffers, and kind of worthwhile one to know because we use it a lot when we compound. It basically has two solutions, okay? It has it of the essentially dibasic sodium phosphate. So the salt form of this Sorensen's phosphate buffer, the salt component is the dibasic sodium phosphate because it's Na2HPO4. Whereas the acid component to the buffer solution is the monobasic sodium phosphate, NaH2PO4. So same thing, we got a salt, we got an acid, okay? The salt is the dibasic and the acid is the monobasic. And it comes pre-formulated, it's already in solution. All we have to do is decide how much volume of each one to mix together, and you're going to see that here in a minute. So that's the two liquids we're going to use as our buffer, but we want to make something. So look on the prescription, it says we want to make essentially an eye solution that contains 30 milligrams per milliliter of ampicillin. So that's our active drug. We have to have that concentration to have our therapeutic effect. So that active amount of drug, of ampicillin, needs to be combined in a buffered solution, and we're going to use Sorensen's to buffer the solution. It says use whatever you need to. And also add whatever amount of sodium chloride you need to make the final product isotonic. So buffer it and make it isotonic. Buffer with Sorensen's, isotonic, whatever needs to be done with sodium chloride. All right. The only other thing I did provide you is that we need to know for the E value, the sodium chloride equivalent value for ampicillin is 0.16. Can you do this? It's kind of cool, right? Let's tie everything together. And again, you could start with the phosphate buffer, or you could start with the ampicillin with isotonicity. Let's just, I like to always start with the active ingredients, so let's determine how much ampicillin we need. For this prescription, we're making an eye drop that has 15 milliliters, right? That concentration is 30 milligrams per mil. So 15 mils times 30 milligrams per mil, mils cancel. I'm in milligrams. Just to convert that to grams, let's multiply by 1 gram over 1,000 mils. So again, doing this, mils cancel, milligrams cancel, and my final units are in grams. And if you do that math, what it's saying is that in my 15 milliliters, to have that right concentration, I need to put in 0.45 grams of ampicillin. Okay? Is everyone okay with that? That's the amount of that I'm going to weigh. I really will weigh that amount of ampicillin. But now, let's deal with the tonicity part. We're going to be using the sodium chloride equivalent method because we were given an E value. So in terms of tonicity, it's not so much important to know how much ampicillin is in there. It's important to know how much ampicillin or how much sodium chloride that ampicillin mimics osmotically. So let's take the weight of the ampicillin that really will be in there and actually convert it to an equivalent weight of sodium chloride. That is, 0.45 grams of ampicillin mimics how much sodium chloride in terms of its osmotic effects. All right? So that's the E value. And I'll still remind you, hopefully you didn't forget, this is super important that you can go from an E value of 0.16 to putting units with it as 0.16 grams of sodium chloride per gram of drug. And by doing it that way, my grams of ampicillin cancel, and I'm now in grams of sodium chloride. So would you agree, 0.45 grams of ampicillin mimics osmotically how much sodium chloride? 0.072 grams. Any questions about that? That's kind of the first part to the isotonicity. All right, we'll skip that. We'll come back to that in a minute, and let's deal with the buffer. All right, so the whole reason about using commercially available buffer systems is they provide you this information. It's beautiful. All right, so you can make a buffer solution with relative amounts of the acid and the salt to get whatever kind of pH you want. So remember on the prescription, what was our desired pH? What's a good pH for ampicillin for the prescription? 6.6, right? So let's go down to this pH table right here and look at, here's my pH of 6.6. If I want a pH of 6.6, how much of my monobasic and how much of my dibasic solution do I need? Remember, if you look on these columns here, the concentrations of each of the commercial solutions are the same concentration. They tell me the relative amounts to combine it with to get the pH that I want. So of the monobasic, I would use 60 milliliters, and of the dibasic, I would use 40 milliliters. If I mix 60 milliliters of monobasic with 40 milliliters of dibasic, shake it all up, what is my resulting pH? 6.6. Yay! But do I want 100 mils? Wait a minute. 60 plus 40 is how much? It's 100 mils. I don't want 100 mils. I'm not making 100 mils. How could I possibly figure out how much I need when I only need 15 mils? Let's just set up some proportions, all right? So what I did is, let's start. Here is the monobasic. So my value here for 60 for the monobasic was to make, I needed 60 mils of the monobasic out of 100 mils total. Would you agree? 40 plus 60 is 100. So I needed 60 out of the 100 to be the monobasic. Let's just set that equal to some X amount over 15, because I don't want 100, I want 15. Okay? So do you all see where the 15 comes from? The 15 is the amount that I want to actually compound. So 60 over 100 is equal to X over 15. Solve for X. What do you get? 9 milliliters. So an equivalent amount, a proportional amount, 60 to 100 is the same as 9 out of 15. And let's do the same thing for the dibasic. So down below there, remember the dibasic needed 40 out of 100. So let's set that equal to X over 15. And I see that that is 6 milliliters. So in the end, this are my final answers for the volumes. I need to use 9 milliliters of the monobasic with 6 milliliters of the dibasic. And 9 plus 6 is equal to how much? 15, and that's my total volume, right? Was that pretty easy to do? But you've got to use the tables to tell you which proportion to get whatever pH you want. And using those fixed proportions that are going to be standardized and not going to be necessarily what you want, you have to reproportion those to get to the volumes you want. So truly, I have now buffered my solution by using 9 of the monobasic and 6 mils of the dibasic. That will be buffered at 6.6. Beautiful. The only thing I now need to worry about is to finish up with the tonicity, okay? So the column that I avoided up to this point was this last column over here. So I've shortened up my table a little bit just to show you what was the one section for the 6.6 there. I know how much to do to make it buffered. What that last column tells me, if you read that carefully, it says the amount of sodium chloride required to make the final product isotonic. Okay, so at the pH of 6.6, using 60 for the monobasic and 40 of the dibasic, you would still need 0.49 grams of sodium chloride to make what volume? 100 milliliters isotonic. So remember, 60 plus 40 is 100. At 100 mils, at that proportion, you still need to add 0.49. But I'm not making 100 mils, so the first thing let's do is let's proportion out. So again, if I need 0.49 for how many mils? 100, remember that's where that comes from. I need 0.49 out of 100. Let's set that equal to X over the 15 that I'm compounding. If I solve for that, that will tell me the remaining amount of sodium chloride I still need to add to be able to make it isotonic. So by solving for X, I got 0.0735 grams of sodium chloride. So is that the amount of sodium chloride I'm going to add? Well, wait a minute. So the only things in there are my 2 phosphate buffers, and I would still need that amount of sodium chloride, but aren't I adding some ampicillin? There's going to be 0.45 grams of ampicillin. So do I subtract 0.45? No, I need to subtract the equivalent amount of sodium chloride that ampicillin mimics. So again, here's the amount that I just calculated here. So the total I need is that. This comes from our previous E value, remember? So we determined that our 0.45 grams was equivalent to 0.072. Subtract that, and what's left is the amount of sodium chloride I still need to add, which is 0.0015 grams. So we're done. Do you know how to compound this? What would your final instructions be? Well, let's weigh out 0.45 grams of ampicillin. Do you guys remember where that came from? That gives us the right concentration of our active ingredient. For 15 mils, that's the amount of active drug I need to produce my therapeutic effect. Right? So I weigh that amount. I also weigh 0.0015 grams of sodium chloride because that's the additional sodium chloride I need to adjust the tonicity. So I mix those solids together and then I dissolve them in essentially 9 milliliters of the monobasic and combine that with 6 milliliters of the dibasic, shake it all up and it all dissolves. Would you agree that the final solution will have a pH of 6.6? We'll have the right amount of ampicillin and we'll have the right amount of tonicity. The last thing we would have to do is take all of that into a clean room, into a hood, and basically sterilize it through filtration. We would take our solution, run it through a really fine filter in this aseptic environment that would pull all the bacteria out. We put it into a sterile ophthalmic container, and we've got our final product. You kind of see why you need to know some of these calculations for compounding. You will eventually have to make sterile products in an IV, and how do you know how to formulate them, and how do you know where the buffers came from? So in the end, remember, because we're about ready to move on, I'm about done, and we'll move on now to electrolytes through this, but the isotonicity and the pH, all of this buffery type solutions are all required to make an actual